Today we are talking about polygons and the sum of the angles in those polygons. We also will talk about and figure out a formula for how many possible diagonals can you draw through any polygon. And then we'll have the chord tangent theorem as a special case of one of the formulas that we wrote down yesterday. So first I am wondering, is there anybody who can tell me the difference between concave and convex polygons? Does anybody know those words? Nobody's quite sure on that. Want to venture a guess? Not a curve because it needs to be straight, but a section that does cut into the polygon. Very good. So concave looks like it has a cave going inside the polygon. Convex does not. Technical definition, if it is convex, every bit of every single possible diagonal is totally inside the polygon. If it is convex, there is at least one diagonal, a line from one vertex to some non-adjacent vertex, that is either entirely outside or at least partway outside the polygon. We are also used to talking about the sum of the interior angles in a triangle. And what do they add up to in a triangle? 180. We can also talk about what they add up to and have a formula for what they add up to in any polygon. You've seen this one before, may or may not remember it. What do they add up to in any quadrilateral? 360, and then we're going to be able to talk about, well, what if it has 21 sides or whatever. New definition, and it looks a little bit strange, exterior angles. If I'm talking about an exterior angle, I will pick one of the sides and I will extend it so that I have a straight angle over here. My exterior angle will be this part that's in here. I could have extended the other side instead, and I would have had a vertical angle that's the same, but we only want one exterior angle at each vertex. I'm going to very quickly draw one at all of the vertices. So now in blue, I have drawn one exterior angle at each vertex. We want to know if we take one exterior angle at each vertex, what will they add up to? So I'm going to draw over these with my dotted pink lines, so then I can pull them back off and see if we can figure out what they all add up to. So let me get these on. So just to make sure it looks like we've gotten them all. So then if I take one from each of these vertices, did not mean to pull that apart. Okay, it's going to stay. Let's see, I'll just work on going around in order here maybe. So I'm lining them up so that they have the same central vertex there, so we can get an idea of what they all add up to. And now that I got all of those in there, what do you think they add up to? So super easy formula, no matter how big the polygon is. If we take one exterior angle from each vertex and put them all together, we will always have 360 degrees. No calculating necessary. So now, next we are going to talk about the sum of the interior angles. So you just told me that if we have a quadrilateral, they will add up to 360. And the way we got there was we picked one vertex. So I'm going to pick this top left vertex, and I'm going to draw all of the possible diagonals just from that one vertex. How many triangles do I have? So when I have 4 sides, I have 2 possible triangles. If I take the angles of one triangle, how many degrees do I have? And if I take the angles from the other triangle, how many do I have? So both triangles, 180 degrees. If I put all of those angles together that I've just shaded, do I have the original angles of the original quadrilateral? So for the quadrilateral, I need to take those two triangles times 180 to get the total measure of all of the angles. Okay, if I have a pentagon, I now have 5 sides. I'm going to pick one vertex. I'm going to pick this one over here farthest to the left, draw all possible diagonals from it. I can only draw 2 diagonals from that vertex, and how many triangles do I get? 3. So if I shaded things, I would have 3 times 180 to give me all of the angles in the original pentagon. Anybody want to predict if I have 6 sides, how many triangles? So 6 sides, we would have 4 triangles. Not sure what happened to my other diagonal there. It disappeared on me somewhere. There it is. So I would have 4 times 180. Okay, prediction, I won't draw the diagonals. If I have 8 sides, how many triangles? And so 6 times 180. In general, what is the pattern? If we have n sides, what do I need to do to get the number of triangles and the number of degrees for the total sum? Callum? Remember that formula from last year? And we will put that in our formula list in a moment also. First, let's figure out our third formula. This is the hardest one of the day. The number of diagonals. So I am going to draw all of them, not just the ones from one vertex. So with the quadrilateral, I'm going to pick my first vertex. I can't draw to the adjacent ones, and I can't draw to itself. I can only, in this case, draw to one like that. So for one vertex, for a quadrilateral, there's only one diagonal. Now I'm going to go to the next vertex, so I will move to the top right, and I can draw this diagonal. Again, I can't draw a diagonal to itself or to either adjacent one. If I go to the third one, I can draw one diagonal, but whoops, it looks identical to one I've already drawn. And if I go to the last vertex, I can't draw to the one to itself or either side. I can only draw across from it, and I've already drawn that one. So what I did was I took all 4 vertices so that I'd make sure that I covered all of them. So I had 4 vertices. For each of those, I had only one possible diagonal, but I drew them twice, so I'm going to need to divide by 2 to get that I only have 2 distinct diagonals. Okay, let's see what's going on if I have a pentagon. Now I am working with 5 sides. So I am going to have 5 vertices that I need to check. For each vertex, I can't draw a diagonal to itself. I can't draw to either of the adjacent vertices. So there are 3 vertices I can't go to. So for this one, I can go, if it cooperates. No, I can go, there would be one diagonal, or I could also go there. So if I have 5 vertices, there's 3 I can't draw diagonals to, but 2 that I can draw to. So 2 diagonals from each. If I go up to the top, I can't go to itself or the adjacents, but I've got these 2 that I haven't drawn yet. If I come around here to the right, I could draw this diagonal that I already have. I could draw one new one that I haven't put on there yet. If I came to the bottom, I've already drawn both of these. And if I came to my last one, I'd be redrawing those 2 remaining ones. So I'd have everything twice. So I'd have 5 vertices. Each of those has 2 diagonals, but I've drawn everything twice. So in general, we won't try to draw these. We look at how many vertices we have. Each vertex has 3 vertices it cannot draw a diagonal to. It can't draw a diagonal to itself. It cannot draw a diagonal to either of the adjacent ones. But it can draw a diagonal to everything else. So it can draw a diagonal to n minus 3 other vertices. If we do that, though, we will have drawn everything twice. So we need to divide by 2. Do you see how we come up with that formula? So let's get these in our formula list now. We had that the sum of the exteriors, one at each vertex, is always 360 degrees, no matter how big the polygon is. We know that the sum of the interior angles, we draw triangles, and if we have n sides, we have n minus 2 triangles we can draw. So n minus 2 times 180. For the number of diagonals in a polygon, we look at each of the n vertices. Each one has n minus 3 diagonals. That draws everything twice, so we need to divide by 2. And that gets those 3 formulas up there for us. The one remaining formula we won't do any examples with today. It's just going to be a special case of one that we saw yesterday. So we are going to have a circle, and we are going to have an angle that has its vertex on the circle. Yesterday we did this where both of these went through the inside of the circle, but the vertex was still on the circle, and we said that our angle was half of the arc that it intercepts. That is also true if it is actually a tangent line. So if this one only intersects the circle at the one point, the formula is still true. The angle is still half of the arc, or the arc is twice the angle. So if the vertex is on the circle, that's the formula, regardless of whether it is 2 chords or it is a chord and a tangent that we are talking about. And then we're going to do one example where we use these top 3 formulas, and then I'm going to give you a shortcut notation that it's okay to use in your proofs, so you don't have to write things out quite as long as the answers in the back of the book will show you. Save you a little bit of writing. I don't think any of you will object to that. So just as soon as everybody has these formulas down, we will go on to that example. Are we almost there? All right, let's give that a try. So we have an 11gon, 11 sides, and we need to do all 3 things: interiors, exteriors, and diagonals. When you're answering more than one thing, I need them labeled in some way which one is which. Let's do exteriors first. Everybody, what will the exteriors add up to? So all we have to do is write down that the exteriors add up to 360 degrees and include the label. Interiors, what is the formula?
N minus 2 times 180.
Excellent, n minus 2 times 180. If n is 11, we are looking at 9 times 180, so help me out. What does that get us?
60.
And we will label that degrees. And label that that was the sum of the interior angles. That just leaves the number of diagonals. So we need our new formula for that. What's the formula for the number of diagonals?
N minus 3 over 2.
Number of vertices, each has n minus 3 diagonals. Draw everything twice, so divide by 2. If n is 11, that becomes 11 times 8 divided by 2, 44 diagonals. It is a lot. I would not want to try to draw them. I would not even do very well just drawing the 11gon. It would end up sort of looking like a lopsided circle, most likely. But it would be a lot. But easy formulas, right? As long as you memorize them and get them correct. Okay, last thing for today. In proofs, if you have a line in your proof that says you have a triangle with 2 congruent angles, that means you have an isosceles triangle which means that you have congruent sides, you can simply jump straight to a step of saying, you write down your congruent angles, given or whatever, then you can simply say these opposite sides are congruent, write out whatever they are, this side congruent to the other side. All you have to write for your reason is isosceles triangle. The book will write it out with a lot of words. It goes the other way as well. If they give you that two sides are congruent, you can simply say that that means that you have congruent angles and your reason is isosceles triangle. Anybody have questions on that?